So to start, I guess I'll have you imagine a world in which people are going about their lives. They're grabbing their keys, they're getting into their cars, they're meeting their friends for coffee, and while people are doing all of this, data is unobtrusively captured. And now imagine that there's a subtle change in these behaviors, and this is reflected in the data that you're capturing. And that we can use the data that we're collecting to determine which individuals are experiencing the initial pathological declines in cognition and functioning. And this goal is especially important in the context of Alzheimer's disease, which of course has an increasing number of secondary prevention clinical trials that are aimed at detecting and preventing the onset of any cognitive symptoms while people are still asymptomatic. Some examples of these secondary prevention clinical trials, of course, relate to the anti-amyloid trials. Of course, you all know some of them are now FDA approved as disease-modifying drugs. And the approved drugs, well, although they clearly demonstrate the removal of amyloid, the clinical meaningfulness of that removal is still somewhat debated. And so one idea has been to go earlier into the preclinical stage when people have the amyloid are present, but the cognitive symptoms are not quite set in yet. And so all of these trials really highlight the importance of why early detection is so important. And so the idea of using real-world data to improve early detection and monitoring of cognitive decline is something that I'm really excited about. I think that there's enormous potential to use technology in very thoughtful and innovative ways to measure cognition and functioning in a way that's externally valid. And I think that the opportunities are only going to continue to grow as technology continues to develop. So with this in mind, my big picture research goal is to use real-world assessment, cognition and functioning, to improve the detection and monitoring of early decline in the context of AD and dementias. So working towards this goal, my research builds upon my background in a couple of different areas that was touched upon in the intro. So I have a background in multimodal neuroimaging. I've been doing more recently amyloid and tau PET imaging, but prior to that, structural MRI and active MRI analyses for I guess about 15 years now. Also my background in neuropsychology, where I'm in the process of getting board certified. And then my background in statistics, where I got an additional master's during training for Northwestern. And with these building blocks, I've been developing a research program that really tries to incorporate AD biomarkers, cognitive assessments, as well as real-world measures of cognition and functioning, with emphasis on kind of the overlap in these areas. Yeah, the overlap in the Venn diagrams. All of that to kind of have the goal of a better understanding of brain behavior relationships, and also validating any new measures of cognition that get developed. And so far, I've done this by leveraging existing large data sets. For example, ADNI, A4 in the Framingham Heart Study. I'll go into a couple of these later on to the top. And I've also been collecting my own data at Stanford through the Stanford ADRC, where I'm a member of the clinical core and the imaging core, and I also work closely with the data management core. I've also been collecting data through the Stanford and Aging Memory Study. This is a cohort that's led by Beth Mormino now. These participants, about 200 of them, were enrolled when they were cognitively unimpaired, and they're now coming back for their 8-year follow-ups. And then there's a small spin-off pilot study called SAM's High Frequency, and I'll go into a lot of details to talk about this. So for now, I just want to take a moment to try and highlight why real world assessments are useful, since I think maybe this is the most unfamiliar part of my research program. In general, I think that real world assessments can help us overcome many of the challenges that traditional neuropsych assessments face. So for example, neuropsych testing, I'm sure many of you know, is quite difficult to access for a large portion of the population. So for example, if you live in a very rural area, you might need to drive several hours to see a neuropsychologist, and that doesn't take into account insurance issues, wait lists, all those kinds of things. But if we can measure real world cognition and behavior in a way that's really low burden, and we can actually use that to detect meaningful changes in a person's behavior, then perhaps that could be used as a screening tool to potentially alert somebody of when they need to make that extra effort into coming in. For longitudinal neuropsych assessments, usually people will come back maybe 1 to 2 years later But of course, that interval is quite long, and there might be really important changes happening during that time. And so another benefit of real world assessments is that it allows for high frequency sampling. So we can measure, changes in cognition or behavior. We can sample at the month scale, week scale, days. You can even get information down to the second. And I'll give some examples of how my research incorporates high frequency data collection later on in the talk, but for now, I'll say that I think the possibility of capturing high frequency data, changes in cognition and behavior on a time scale that's much shorter than months and years is really exciting. And I think it'll likely give us some new insights into how cognition develops or changes in the context of AD. And then finally, one other challenge is the use of non-representative norms. So to interpret our neuropsych data, we have to compare to norms that are developed, most of which are developed in highly educated white individuals. That makes it quite challenging if you have a participant or a patient that doesn't come from that background. But if we can find, again, low burden ways to capture changes in cognition and functioning, in the real world manner, it's easier to get that data longitudinally. So then it's potentially easier to use that longitudinal data as a comparison point. So comparing the person to themselves rather than a person to a large norm. I'll say that importantly, I don't think that real world assessments should replace comprehensive neuropsych testing. I think comprehensive neuropsych testing definitely has its place and its usefulness. I think these opportunities for real world assessments can actually complement or provide additional information, but not necessarily replace neuropsych testing. So for today, I'm going to talk about 3 different areas of my research, and I'll start with some work on PET imaging. And I think everybody here is quite familiar with Alzheimer's disease, but just to make sure everybody's on the same page, I'll just say that the neuropathological hallmarks of AD are the formation of these amyloid plaques and neurofibrillary tau tangles. And importantly for my work, amyloid and tau PET can be imaged in vivo using PET imaging. And so when we use these imaging techniques across the different clinical stages of Alzheimer's disease, shown here on the x-axis, we can see when and to what extent these changes become, when they occur and when they become abnormal. So for example, the first thing that we know happens is amyloid positivity is the first change to occur. And this can occur decades before the onset of any cognitive symptoms. Amyloid plaques tend to be distributed pretty widely throughout the cortex, even very early on in the disease course. And then we see elevated tau PET signal, and the location and the severity of the tau PET is really important. And it's a stronger predictor of cognitive ability and future cognitive decline in comparison to Amyloid. And then these tau abnormalities are followed by neurodegeneration, changes in cognition, and then changes in functioning. And I mentioned that regional tau is really important. So here's a nice example of why regional tau matters. And this paper was just published this month, a couple of weeks ago. And so for this study, we used the ADNI data set, and we looked at individual scans, and we noticed that looking at this is an individual tau PET scan. If you're not used to looking at these individual threshold and tau PET scans, just pay attention to the colors, and that kind of shows where the tau signal is. When we were looking at the individual scans, of course, there are people who have this kind of typical AD pattern where tau deposition is predominantly located in the medial temporal lobe, extending out to lateral temporal and lateral parietal regions. But there are also individuals that really show this striking asymmetry. So here are 2 people, one with much more left tau than right tau, and then the right side, an individual with much more right-sided than compared to left-sided tau. There were also people who had this typical AD pattern, but also had frontal tau, again with this asymmetrical pattern. And then other individuals with tau primarily in the anterior temporal regions, again with the asymmetry, so either left or right, much more prominent. And then also posterior cortical is this asymmetry as well. So focusing in on this asymmetry, we actually identified 27 participants who had this extreme left temporal pattern. So much more tau in the left hemisphere than the right hemisphere. And then we also found 20 participants who had extreme right temporal asymmetry. And the groups here are defined by 2 standard deviations greater than the mean in terms of their laterality index, but all these analyses and the results, we looked at continuously at those holds, it holds there too. Interestingly, when we compare the cognitive and behavioral profiles of these 2 extreme groups, we can see kind of a double dissociation in terms of language and behavior. So first, in terms of language, we see that the more tau burden in the extreme left group is associated with reduced language functioning, but that's not present in the extreme right group. And in contrast, when we looked at behavior measured by the neuropsychiatric inventory, the more tau burden there is in the temporal cortex, the more behavioral disturbances there were in the extreme right group. But again, that's not seen in the left group. And these patterns were not present when looking at memory and executive functioning, so it seems to be really specific to kind of language left, behavior right. And again, we looked at this continuously, and the same pattern was present there too. So I think this nicely highlights how different tau patterns have implications for symptom manifestation of disease. And we can also see that even in the preclinical AD stage. So as I mentioned in the very beginning, preclinical AD defining here as those who are cognitively unimpaired but have abnormal amyloid, so amyloid positive. And again, this phase is really important in the context of clinical trials, where many trials are trying to are focused on this stage and kind of highlighting the importance of why it's important to understand the earliest changes, both in terms of tau and then also in terms of cognition. So focusing in on this preclinical stage, we really wanted to understand what are the regional tau patterns here, and does it have a consequence for the cognitive profiles. So we published a study using the A4 data set a couple years ago now. The A4 study was a secondary prevention clinical trial, so focused on cognitively unimpaired individuals. It was a failed trial, and a subset of them had tau PET imaging. We leveraged that data. So a group of the participants here were, I guess you can say, normal, so amyloid negative, and they also didn't have much tau burden. This again is a tau PET, now a group tau PET image. And if you're unfamiliar, again, with looking at this, the hotter colors indicate more tau signal. But if you look at this, you might think like, man, there's a ton of tau in my basal ganglia, so that's mostly where we should look. But with tau PET, you have to be mindful of off-target binding. And so the signal in basal ganglia represents off-target binding. So as you look at these images, just kind of ignore that hot spot there. But if you look at the rest of this image, there's not a whole lot there, because by definition, they're amyloid negative, they're also tau negative. In contrast, there was a group who were in the preclinical AD phase, so amyloid positive, who also showed significant tau burden in the medial temporal lobes. Kind of see the yellowish color here. Oh, the mouse doesn't work, but in the medial temporal lobe, there's some yellow there. So this is kind of based on the Brock staging and neuropath literature. This is kind of the group that shows the expected tau deposition. So we know that the medial temporal lobe is one of the first regions to accumulate tau tangles. This is kind of the traditional preclinical picture.
The base of the midbrain, is that off target or is that real signal? You know, the base of the.
Oh, yeah, off target. Interestingly, for this study, we also actually found that 9% of the preclinical group had substantial cortical tau burden. This was not really appreciated before. And within the 9% of the preclinical group that actually does have substantial cortical tau burden, you can actually cluster them. So 2 of the sort of subtypes have this asymmetrical pattern that I talked about in the previous study, where there's much more tau in the left or the right hemispheres. And then there's also a subgroup where there's substantial tau accumulation in precuneus as well. And I want to reiterate here that these participants, even though they have a lot of tau PET signal in the cortex, they're still cognitively unimpaired. And so when we look at the cognitive profiles of these different groups, you can see some subtle but significant differences. that again highlight that the location of tau deposition impacts the cognitive profile even in this very early preclinical stage. So if we do the comparison between the kind of normal group shown in gray, those people who are amyloid negative and don't have much tau, in comparison to the preclinical group with medial temporal lobe tau burden, we see the expected deficits in memory, but their performance and executive function is comparable. But when we look at that cortical group, so in the preclinical group with additional cortical burden, we see a similar reduction in memory, but then we see this additional deficit in executive functioning. Again, really highlighting that this tau burden is impactful even very early on. So here we show that the tau burden and location of tau burden is important for cognition, even in the preclinical stage. And although there's significant differences between the groups, the differences are subtle, and so this sensitivity for detecting these subtle cognitive changes could, of course, be improved. And I'll just take a brief detour to say that, so in addition to the very interesting and cool findings, one thing that I really loved about this project was that we were the first to process the A4 tau PET data. And because of that, we were actually able to return that data back to the A4 study team and then put that data on Lonely. So that data is available for anybody to use on Lonely. And there's been a couple of papers now of other groups using that data and to look at whatever it is that they're interested in looking at. And it's been very cool to see people using the data that we processed. And similarly, I've also been processing the amyloid and tau PET data for the Framingham Heart study. No papers coming from that yet, but hopefully soon. And I've also been kind of involved in building the local infrastructure at Stanford to help us share the imaging data in a more efficient manner. So for example, I've been working with Flywheel to share the imaging data that's been collected for the Stanford ADRC and also for SAMS for people who are interested in looking at the actual images. And then for people who just kind of want a value, Centiloid value, tau PET value, we've also built a pretty robust REDCap that gets updated in real time. So if somebody involved in the ADRC wants to know what is the Centiloid value for participant 500, they can easily look this up, and this gets updated within a week of the scan. So that's been really nice to see. I'm
curious, what processing software are you using?
Yeah, we built a local pipeline that's based on FreeSurfer.
It uses the MRI.
Uses MRI, yeah. So the data that we collect at Stanford is PET MRI. So yeah, we leverage that MRI there. So processing and sharing imaging data sets both locally and also with larger data sets is something that I'm really interested in and something that I hope to do.
What's the spatial resolution of the tau PET? Is it still rather large voxels?
Yeah. I think coming from the MRI, fMRI space into PET, the first time I saw a PET image, I was like, I'm not wearing glasses or can't see anything, but yeah, it's not great. But I think the PET MRI, you could argue, helps a little bit, because at least it's being collected at the same time, so the co-registration is theoretically perfect. So I'll switch gears now and talk a little bit about looking at my work looking at different speech patterns in the context of aging and AD. And for this, I'll say that I was kind of inspired by clinical anecdotal observations where sometimes it seemed like patients would come in and they could very quickly recall the information that they were trying to tell me. And sometimes they might have better memory scores, whereas other patients come in, they got lost in their train of thought, or they couldn't quite remember what it was that brought them in. And sometimes they did worse on memory testing. So I really wanted to delve deeper into kind of what can different speech patterns tell us about cognition. All right, so I'm taking a step back. So storing memory tasks, like logical memory, of course, are one of the most common ways that we assess memory functioning in AD research. And so these tasks involve telling a short story to the participant or the patient, and then after a delay, asking them to recall that short story in as close to the same words as possible. And then to score those responses, we then just look to see if certain keywords or phrases were said, and then we tally up the number of keywords. So in this case, this person would get a score of 19. But as you can see here, there's a lot more information that we're not using. So and we can do a lot more than just kind of tally up keywords. And one thing we can do is parse the participant's response into utterances. And an utterance is a small unit of speech that's defined by a complete sentence, a long pause, a change in intonation pattern, an expression of a different thought, or a change in speakers. And if we do this, we can then quantify the amount of time that somebody's spending speaking in an utterance. So kind of what I'll call utterance time, and this reflects the amount of time that somebody's spending speaking in a complete thought. Okay? And by parsing into utterances, we can then also look at between utterance pauses. And it's possible that these between utterance pauses actually are a reflection of memory ability. So you can imagine that as you finish telling a detail.
How many people are thinking of the debate right now?
Yeah, exactly.
Please don't run this analysis.
Yeah, so things that are noticeable, I think, to a large portion of the population. Yeah, so, of course, it's intuitive. If you're thinking of a detail and you might need some additional time to think of the next thing that you're trying to recall, and you might need even more time if your memory function is not there. So we can now quantify the amount of time that people are spending in these between utterance pauses, as well as count up the number of pauses that people are making. And then we can also look at how fast somebody is speaking. So simply words per minute. And this might tap into processing speed, executive functioning domains. And then we can also look at the percent of unique words that people are using, which might give us some insight into the amount of repetition that's occurring. And so both my K99 and the Alzheimer's Association grants are trying to look at speech as a novel marker of cognitive decline, with the hypothesis that one or some of these speech metrics might actually be a sensitive marker of amyloid and tau in cognitively unimpaired individuals. And so to test this hypothesis, I first established a relationship with Rhoda O, who's the director of neuropsychology at the Framingham Heart Study at BU. If you're not familiar with this study started in 1948 with the original goal of understanding cardiovascular risk. And then they followed that original cohort. They actually started also following their children and grandchildren. So there's actually 3 generations worth of data now. And then importantly for me, starting in 2005, they started recording their neuropsych assessments, not for the purpose of looking at speech patterns, but actually just to help with scoring and fidelity. But we can actually use those recordings to now look at speech patterns. And then in 2015, a subset of participants also got imaging. And so now we can look to see how these speech patterns relate to the AD biomarkers. And so this is our first manuscript from that project. Here we looked at the 237 participants who did receive tau PET imaging and then their closest neuropsych for this cohort. One thing I'll point out here is that Framingham Heart cohort, the age range is 32 to 75 with a mean age of 55. So this is very different than ADNI, A4, which tends to have a mean age of 70 or so. So different cohort, and because of this younger age range, much fewer of these participants are actually input positive. So here, 8% of them are input positive. So just keep that in mind as you are digesting the next few slides with these results. So as part of the neuropsych assessment, participants completed that logical memory story recall task that I described earlier. And then thanks to Nikki Smith, who was a research assistant who is now at Cambridge, just started grad school at Cambridge, we were able to transcribe the recordings and then look to see how the traditional delayed recall score related to these different speech metrics that we lab. So we first looked at utterance time. These you can probably imagine, the longer somebody spends speaking, the better their delayed recall score. For between utterance pause time, there's actually no significant relationship with the delayed recall score. For the number of between utterance pauses, there's a significant but very weak relationship. So the more pauses somebody's taking, the better their recall score here. And then for speech rate, again, significant but weak relationship. So the faster somebody's speaking, the better their recall score. And then lastly, the percent of unique words, again, significant but weak relationship. So the more repetition, the better. And then as far as the speech metrics in and of themselves, they have a moderate correlation with each other. But the thing I want to highlight here is that for most of the speech metrics, they're actually not very strongly related to that delayed recall score, right? So they're giving us information that's different than the traditional way of scoring this delayed recall.
Sorry, what were these correlations between these unique measures that you have and what else?
I'm focusing, if you focus in on, actually.
Logical memory.
Yeah,
Oh,
logical.
the normal logical memory. So it's all episodic memory correlated with these types of speech metrics.
Yeah, exactly.
Okay.
That's the top row there. But you can also look at like the different correlations with the speech metrics and like utterance time and pause time or something like that. But I think the most interesting thing is that top row up there.
Okay.
So, yeah.
Could you combine different indices to try and not the predictor? Maybe you can show some.
Yeah, yes, I didn't combine the speech metrics yet, but that's something that we're looking into. And also looking, I mean, these are five speech metrics that we kind of pulled out as a first pass. But there's a lot more, even things like prosody and like acoustic information. That's something that we've started to do as well. So then the next question, of course, is whether these speech metrics relate to amyloid and tau. And here we see that neither the delayed recall or any of the speech metrics actually show any differences between amyloid positive and amyloid negative individuals, possibly because that amyloid positive group is so small. There are only 18 participants in that group. And then similarly, when we looked at the delayed recall associations, here I'm showing entorhinal tau on the x-axis with delayed recall to that traditional logical memory delayed recall score, there's no significant association there either. But then when we look at the speech metrics, here we do see some significant associations with 3 of the 5 metrics. So higher tau burden is actually related to longer between utterance pause time, to more between utterance pauses, and also to slower speech rate. And this is true if you look only in the amyloid negative group, so suggesting that's not being driven by the presence of these amyloid positives. It's true whether or not you account for various covariates. So it's a pretty robust effect, surprisingly robust effect. That's kind of nice to see.
It's not driven by some outliers. Let's look at the scatter, not really.
Okay, so then we next wanted to look more carefully at the 3 different speech metrics that did relate to tau to try and understand the cognitive mechanisms that are kind of driving that speech pattern. And so to do this, we used a bootstrapped bridge regression procedure. So we took all of the neuropsych scores, the traditional neuropsych scores from the comprehensive neuropsych battery, and used that to try to predict each speech metric. So not combining the speech metrics, as you mentioned, but the other way around. And so when we do this, we actually see that these processing speed measures like trails A coding are the best predictors of between utterance pause time, whereas kind of encoding, memory, working memory measures are the best predictors of number of between utterance pauses, and then memory and processing speed measures are the best predictors of speech rate. But again, I want to emphasize that the other neuropsych tests only explained a very small percentage of the variance in terms of the speech patterns. So it's not like you can just kind of get the same information by giving a comprehensive neuropsych battery. So this is kind of tapping into something that's different. So with this initial study, we showed that speech patterns during memory recall are associated with the cognitive decline that's associated with early AD pathology. And the study that I just went over is the first step, so that's part of the P99 part, where we're looking at speech in a very circumscribed manner, right? This is in the context of a neuropsych assessment. It's a clean environment, there's not a lot of distractions. The responses that you're going to get are very limited. Right? Generally, people aren't going to talk about anything if you're given a prompt. And so the next step to kind of move from the lab to the real world is part of the R00 phase, where we're going to do still neuropsych testing, so still a limited prompt, but do so in the real world using smartphone-based cognitive assessments and getting speech samples in that way. And then I'm planning on writing an R21 to then look at, to better understand speech in different contexts, and now not only speech in the neuropsych context, but also kind of more of a conversational free speech pattern. So how do those speech patterns change, or how do they stay the same when the context changes? And I've collected a little bit of preliminary data, looking at this from the SAM study. So these are more people who are cognitively unimpaired coming back for follow-up now. And this graph, you can see, so the different contexts are going to be on the x-axis. And then in this particular case, the utterance time is on the y-axis, and each line is an individual. So we have 5 participants here. And you can see that across the immediate recall context of 2 different stories, the amount of time people are spending speaking is quite constant. And that's also true during delayed recall too. So they're kind of spending the same amount of time recalling the story every single time it kind of comes up. But then when we ask them about, can you tell me the story of the 3 little pigs? Can you tell me about a pleasant memory? Or tell me about your daily routine? The amount of time people spend speaking kind of goes up. That probably is obvious. But then we can look at things like, the percent of time that they're actually spending in pausing, right, across these different contexts. And here we see kind of a slightly different pattern. So there are some participants who are relatively stable across contexts, like this red person here, whereas there's other people who are maybe spending less time pausing, or more time pausing in the memory context, delayed recall context in comparison to free speech. How this relates to memory scores, I don't know yet, it's only 5 people, but kind of exciting preliminary data for giving. And hopefully that'll set up an R01 nicely, where we can then look at how speech patterns vary or might look during unstructured speech and how that relates to AD biomarkers. So perhaps we could record phone conversations between study staff and a participant, or even between a study participant and their study partner, if both people agree to that. And then understand how these speech patterns help with early detection of amyloid tau deposition, or perhaps even how these speech patterns might relate to different regional tau patterns. Something down the line. Okay, so now I'm going to switch gears and talk a little bit about my work on item displacement. And did you?
Well, I'm amazed because I'm thinking all this stuff that's about ready to happen at the hospital setting, where they're talking about putting in kind of ambient listening devices to write your notes, so that the physician can spend time just talking, and the AI, crazily enough, will essentially code what happened in the visit. And you can imagine the kind of data that you get. If that
would be
takes
really
place,
cool.
it's kind of very futuristic, but this place is trying to do it as is on the edge of that as possible.
Yeah, if the actual recordings.
I know.
That would be like
It's
the
gonna be a
gold
bunch
mine.
of
Yeah.
challenges and everything. but,
Yeah.
but it's amazing.
You wouldn't even need to know what the words were if you're just
Yeah.
interested in this pause rate
Yeah.
thing. You could listen to the silences and
Right,
if you wanted to get around people that way.
yeah.
It's gonna be an interesting area for sure.
Pause rate and speech rate, yeah. Code.
Know what they're saying.
Yeah, exactly. Yeah, well, similar to that kind of ambient monitoring, is the work that I'll talk about for the item displacement. So here again, this is kind of thinking about like clinical observations, where sometimes if I ask people, what brings you in today, sometimes the response I would get is spend my keys ever, and like I can't find anything, losing my glasses constantly, and so I wanted to try to better understand that phenomenon of losing things. And as you can probably guess, item displacement is pretty common in older adults. So here's a study of the A4 study looking at 4,500 unimpaired older adults. And you can see that about 20% of participants are reporting, yes, I'm definitely misplacing things more often than before. Another 20% are saying maybe to that, and that's corroborated by their study partners. So this is like clearly visible behavior that's not only obvious to the participant, but also to the study partner. And interestingly, importantly, those who have abnormal amyloid again, in the preclinical AD stage, are significantly more likely to endorse that yes or maybe to their question. And so this kind of suggests that item misplacement might be a candidate for early detection of AD. And then additionally, item misplacement is also clinically meaningful. So here's a somewhat old clinical trial where they enrolled 130 patients with mild to moderate AD, and then during a clinical interview, 75% of them, of the patient or study partner, actually spontaneously reported item misplacement as something that is occurring. So they weren't specifically asked about it, but they described that as something that is problematic. And then about half of those actually reported it as a treatment goal. So clearly something very meaningful to patients and their families. And so given that item misplacement seems to be associated with biomarkers, it's also clinically meaningful, it seemed kind of worthwhile to better understand this phenomenon, with potentially the ultimate goal of developing some sort of measure that could be incorporated into clinical trial, potentially clinical trial outcome measure. And so I was lucky enough to have this idea funded through an R03 equivalent by New Vision Research. This is part of the Charleston Conferences on Alzheimer's Disease. And I'll describe that study now. So the goal here was to try to develop an objective marker of item displacement. And so I partnered with some folks at electrical engineering at Stanford to develop this system that uses these little tags. So these tags are these Bluetooth low energy proximity sensing technology. Lots of words, but you can think of like an AirTag. AirTag does a little bit more than this. Yeah. So they're very small. You can see, about 3 centimeters here. And then we're actually attaching them to various items in our that the participants own. So this is the SAMS high frequency study. We're attaching them to participant keys, their phone, their glasses case if they have one, their wallet, and a TV remote. And then these beacons constantly emit Bluetooth signal. And that Bluetooth signal is then picked up by these microprocessors that we've installed. So ESP32s, they're kind of also very small, cheap devices, kind of like a small computer basically. And all they're doing is capturing that Bluetooth signal and uploading it onto a data server. And so then this is done pretty much constantly. And then we have that signal data that then we can interpolate the distance to each microcontroller and then kind of triangulate the location of that. And so when we do that, we can then, this is real data from one of our participants, a 90-year-old amyloid negative male. We can then get a kind of a map of where these items and how they move in the participant home. So there are some items like the red item here, which are the keys that are constant.
Oh, I thought that remote was on the couch, but no, it just left the couch.
Yeah, so, right. And then other items which don't move a whole lot, like the blue one, the remote, it kind of has a small radius of where it goes. And yeah, so now we have an item map, basically, and we can do this right now. We're kind of doing on the minute by minute scale, but we can adapt that to whatever is the resolution that we will ultimately need. And then we're also asking participants to report in real time when they lose or find one of these tagged items. So whenever they lose or find an item, we've actually programmed and installed Google Nest devices. So they'll just say, hey, Google, I lost my keys. And that gets picked up by the Nest, which then records the timestamp of when that happened, what they lost, and whether they lost or found that. And so then, of course, we can look to see, okay, at that particular time, the keys were in this particular location, which is like very outside the norm of that location. And that's why they lost it maybe. And then we can also calculate kind of a more real-time measure of how long it's actually taking for people to find stuff. So this is kind of a more objective measure of item space potentially. And then we are doing a one-time questionnaire to get some subjective reports of item displacement as well. So
they say, hey, Google, I lost my keys, but it won't tell them where they are.
right. Yeah. Yeah, that was actually
Thanks a lot.
Yeah.
Recorded.
And you send them a picture of that map, it's like, under the couch.
Well,
Yeah.
yeah.
Yeah, exactly.
It's just like,
Yeah.
I know where it is, but I'm not.
Right, what is something that didn't interfere with their, like, like an AirTag you can actually use to help you find something. but this is not helpful to them in any way. But it's helpful for us.
Would you like to de-enroll from the study and know where your darn keys are?
Right. Yeah, yeah. Yeah, so we're also asking, you know, how often are you losing things? Are you losing things more frequently than before? And how long do they think it takes them to find it? So I think there's probably going to be a pretty big discrepancy between the subjects, you know, as it's happening in real time versus what they kind of recollect in their memory. And we're doing this importantly at the item level. So currently, when we put the existing studies, there's not many on item displacement, but usually it's just like a single question. Are you losing things more than before? But this probably varies a lot depending on what item you're talking about. And so this will kind of give us some insight, maybe what items are the most focused on. And then we can also look at, we're also incorporating this EMA approach, so we're to better understand how mood and fatigue might affect item displacement. So for 1 week, we're texting people 5 times a day and asking them to rate how happy, sad, tired they feel. And then also if they've lost anything since the last assessment. So it's 35 assessments, which sounds like a lot, but each assessment takes about a minute, no more than 90 seconds. So we've actually had really good clients so far. So we have 3 participants who have completed at least 90% of the assessments, some of which are 100%. And then we have 1 participant who did 50%. So that was those participants as well. And so one really exciting thing about this study is the wealth of information that we actually have. So the item displacement part will go on for 6 months. But because the SAMS high frequency study is actually drawing from a larger SAMS study, we actually also have comprehensive neuropsych testing on these participants already. We have tau PET imaging. They also have CSF information, so we can kind of combine all that together. We're also, and also in collaboration with Beth and Joe Weiner, the Simons Foundation, we are also doing monthly blood draws from these participants. We're doing computerized cognitive testing as well as iPad cognitive testing through the TabCat, developed by UCSD. We're getting actigraphy over the whole year. And then hopefully soon we'll also get GPS information through Florida. So tons and tons and tons of information, which kind of, we can do a lot of different things with. But one downside is that most of these participants are still cognitively unimpaired, and they are not necessarily demographically diverse, so primarily white, highly educated individuals. And so I'm thinking about writing another grant also to kind of expand this to more diverse samples and potentially also move into non-cognitive impairment where item displacement might be happening a little bit more frequently and also more impactful there. So in summary, I hope that my talk today really illustrates the importance of understanding the effects of regional tau patterns on cognition and functioning to help improve the early detection and monitoring of Alzheimer's disease. And that I focus on the intersection of real world data, neuropsych data, and multimodal imaging is something that I'm really passionate about. I think that there's a lot of experts in these domains here at UCSD, so I think there would be a lot of opportunity for really exciting collaborations that you have needs. And with that, I'll give thanks to Beth Rubino, Kathleen Poston, and all the different lab members, the trainees, many of which have now left and gone on to grad school and then funding sources.